Fine. So I said just slightly out of band, but I thought it'd be useful that people asked about this, and I forgot to do it in the last session to go through if this is going to work. Is it going to work? Again. Okay, so here I am. I'll do the C version. So if I go to the MPI version of the model, I just want to reproduce basically in the, let's say, traffic lib.c what was done in the traffic lib.c with on traffic lib.c, and in fact, so the top one is the MPI. All I need to do is copy the stuff here. So I just need to basically, so I'm just saying, okay, I have an MPI process, and now I'm going to assume that there are cores available to do the parallelization. In fact, I think that's it, isn't it? That's basically it. Okay, so that's that done, and literally the same as the OpenMP version. And also, I need to do. In fact, if we they may be the same now. If I diff them. Okay, no, they're almost the same. It's just that I have included. I haven't included OMP.h. Okay, there we go. That's another thing I need to do. Traffic lib.c. I should probably include maybe don't need it, but there we go. Let's include OMP.h. And the other thing is the main traffic.c. As I said, it may be surprising. We could discuss it if you want, but you need to now let's put this in, so we are actually printing out. Now it's very, very important that you print things out, because it can get very confusing. So whoops, no, it can get very confusing if you don't do the right thing. In other words, so we should print out as much as possible. So now, within this rank 0, previously I want to basically say, I should maybe get my indentation correct. Processes each with %d threads, and that is going to be, is it size I've called it? Probably size. Okay, so that's basically it. But the main one I want to do is the copy back. As I said, maybe surprising, but you need to have that copy back parallelized as well for performance reasons. So that's, oops. There we go. Hashtag MP parallel 4. So actually, I think that's basically it. Now let's see if we get the make file correct. It needs to be cc get, let's do O3 minus F OpenMP. That should basically be it. So let's clean, let's make, okay. Okay, so the reason it didn't work is I missed one thing. I forgot hash include OMP.h because I'm calling a library routine. And there's one other thing. Okay, fine. In the OpenMP version, the length of the road is called n cell, but in the MPI version, it's n local. So I need to say shared n local. That was the other difference. So remember that it was complaining about that. So I'm doing it live here, but there we go. Okay, so let's just copy. Now running this thing is going to be the difficulty. So I gave you this ARCHER2.job. And what this does, for example, is it says, let's call it traffic. So it asks for 2 nodes, and it asks for 32 tasks per node. Now we're going to run 4 OpenMP threads. So that means we need to space out the processes to leave gaps in between for the threads. And the way that you do that is you say CPUs per task equals 4. Okay, let QS equals standard. I think it's TA033 under 187 today. Okay. And so now what I'm going to do is I'm going to run this XT high executable first, which just gives me the distribution, and then I'll run traffic. So let's just see if that works. Let's do /traffic, just be careful. Do you think this is going to work? It's not, have we got a problem? Okay, we've got something here. Very quick, a bit surprising. Let's see what this said. So first of all, this was the affinity. So did I get any output? I think I probably had them. Okay. There you go. It seemed to work. It says node 0 has, this is just the XT high, is this node 101, and we have 32 MPI and 4. That's what we wanted. And if you look, the affinity rank 0, thread 0 is on core 0, and it's exactly what we want. Rank 0, thread 0, 1, 2, 3, and then 4, 5, 6, 7. This is exactly what we want, all the way up to rank 32, rank 31, thread 1, 2, and then we go on to the next node, and it's the same there. So that was all okay. Okay, and then it said it did 1100 megacops. Doesn't look particularly good, but yeah, 64 plus each with 64 threads, but we were split across 2 nodes. So we can compare that with what you can do here. We can do a few. We can actually do. We can just actually. Well, that's going to be a bit difficult. Let's do a. Let's just do a series. So we'll see what the speed of that one was. That's the pure MPI. Oh, it's not finished yet. Okay. Okay, so I was that with 366 megahops, and actually this went faster. Okay, that seems. If we diff them, so they should be identical results, but if we diff them, where are that? That was my. What do we get? Okay, so they are okay, fine. The reason why they're not the same, and they should be the same, is that the size of the road isn't divisible by the number of processes, and that's, I don't check that. So let's make it 128,000, and we can show it for, okay. So that's, I believe that's one, and I don't check that, which is a bit naughty, but it's still meant to be a simple program. So there's the traffic.out, okay. And then we'll see again. Let's do node equals 2 tasks per node. I said 32. CPUs per task equals 4. MP non-thread equals 4. Okay, there we go. And if we, we can diff them. Now, if these are different, then there's a bug in the code, and I'm going to have to check it. There we go. So so they do produce the same answer, okay? And actually, the hybrid MPI OpenMP version was faster, presumably because it's such a tiny problem. I'm I'm not entirely clear why it's faster, but it is. There we go. We got the same answer. It was 3 times faster. So I mean, that's interesting, actually. Okay, but that's how it works, and that was a great success. I wasn't expecting that. I haven't actually done any systematic scans on ARCHER2 of this kind of thing. I mean, for this simple code, but that was very, very interesting, actually. But you can see we've got exactly the same answer. What you wouldn't expect is for this to if I said, for example, if I did this, I suspect this would be quite bad. Task per node is 1. This is the extreme. This is 2 MPI processes and 128 threads. 3624. So it was 1,000 megacops as opposed to so it's slower. It's still reasonably okay. Anyway, so it's a very, very toy problem, a very simple example. But you can see that. So the idea is, you take your MPI code, you identify computational loops, and this is particularly simple. This is such a trivial code. There's only 2 computational loops. You parallelize them with OpenMP. Then you launch them in the correct way, and there's a script which does it. It does a number of things. It makes sure that the processors are on the right nodes, that the processors are spaced out, so that the threads fill in the gaps, and that they're all pinned to the cores and don't wander about. All that is done through a combination of srun and sbatch options, and then you get a code which magically runs a bit faster. So yeah, that's basically. So are there any questions on that? I thought that would be useful to do before I do the final lectures. Yeah, so what was your question, Christian? You can do it in audio if you want, or up to you, or do it in chat. Oh, fine. Okay, sorry. Okay, which is good. Okay, so I'm going to do these lectures relatively quickly because I appreciate it's been quite a tough course. It's very, I don't know, for those of you in the UK, I don't know about Europe, but in the UK it's spectacularly good weather at the moment. I'm sure people would rather be outside than on an advanced MPI course, but I will go through these and I'll explain at the start what the purpose is. So what we're going to do, that's the wrong window. Is look at intro RMA. So, as I mentioned in some of the introductory talks, way back in MPI 2 from the late 90s and then reiterated under MPI 3, there was a method of doing remote memory access in MPI where you could do, they were called puts and gets. You could directly read and write put data or read get data from another process. So this was not shared memory, remote memory access, but it's related. And that, in my opinion, is not particularly useful model. I wouldn't even call it message passing, to be honest, but it's there. But then what they did is in MPI 3, they actually extended it, MPI, to allow you to do direct reads and writes to shared arrays like you do in OpenMP. However, they extended the existing put-get remote memory access model. And so we need to cover the basics of that to get on to how we're going to do shared memory. So this, I'm not really concerned about how to do remote memory access puts and gets, because I don't think it's particularly interesting, well, particularly useful in practice, but I need to cover the basics to motivate the next lecture. And so we'll start off with how remote memory access works in MPI. And I think I'll just check I'm still recording. Yeah, and I'm not sharing. Apologies. So this is a very quick overview, okay, but enough for us to get going. So YMA terminology, program flow, and getting started. Okay, and we're not going to do the practicum. So the basic concepts are in MPI remote memory access, it's called the single-sided model, because rather than having matching puts and gets, if you're doing a remote write, only one side, the origin, does a put, or in the other time, if you're doing a remote read, you do a get. So remote processes, excuse me, do not actively participate. There's no matching receive or send needs to be performed. But synchronization is a major issue. And what they did is to provide some safety. You don't want any random process to be able to write over your entire memory. They introduced the concept of a window. So what you do is you create a shared, a window of memory, which is then made available for global remote memory or single-sided access. So windows are the key concept we're going to take forward for when we're going to do genuine shared memory. Now remember, this works across the network. Clearly it'll be faster on and over. The point about this is it's direct read and write to memory, but potentially across the network. So any process can do this to any other process, but of course it's not particularly quick because it's a function call and it has to go over the network. So the motivation, there's a couple of motivations. I mean, one is that many supercomputer networks actually, at their very basic level, actually this is the model, you can actually directly read and write memory across the network. And also, I don't want to go into the details, but some algorithms are naturally single-sided. Often you know where you want to put data, but the receiver doesn't know where it needs to go. Why can't you just write the data where it needs to go without having to tell the receiver, when you get this data, put it here and then send it? So there's a hardware and software motivations for extending the message passing model. So, you know, these one-sided communication function interface to our MPI RMA. I mean, colleague who wrote these slides, Nick, thinks that one side's a confusing term because actually, the problem with the single-sided model, the remote memory access, is you have to worry about synchronization. And so, in fact, the other processes, the remote process may not be directly involved in the transfer, but it has to be involved overall to synchronize. So it's really not as simple as it might seem, but there are some. It's not a silver bullet, and in fact, I'm not really a fan of it, but I'm just motivating it because we need to understand memory windows. So terminology. Now, if you do a send and a receive, it's clear that the data starts on the sender and ends up at the receiver. But when you can, if you want to transfer data from A to B, A can either write the data or B can read it. So you have a number of different concepts. So we have the concept of the origin is the process initiating the request, and the target is the process whose memory is accessed, okay? So, by the origin. Okay? So that may be the origin. That may be where the data starts up or end. That may the target is the whose memory is being accessed, and all the remote access performed on windows of memory. And also all puts and gets are non-blocking. So you have to have synchronization to check that they're complete. And it's not done through waits as it is with normal non-blocking calls. So the RMA flow is you collectively initialize a window where you publish your memory for remote memory access. There's this concept of RMA epochs. It gets quite complicated, but basically you do a synchronization, you issue communication calls, puts and gets, and then at the end you do another synchronization. And then when you only know the communications are finished at the end of the second, after stage C, and then you can collectively free the window. So getting started, we've got to talk about window management, which is really the most important thing, and fences, which is also the same. So we're going to reuse window management and fences when we talk about direct shared memory access in MPI. So you need to create a window. It's a collective call issued by all the processes in the communicator, and what you do is you have an array which has a base pointer. You say how much data it is. This is how big the malloc was. This funny variable MPI AInt is just because this could be more than 2 gigabytes, so it can't be an integer. And the displacement unit is some attempt at doing portability. When we access Windows, we'll say we want to access location 3 or location 7. That is multiplied up by this displacement unit. So for example, if this was an array of integers, displacement unit would naturally be 4, because that would count 0 would be the first integer, 1 would be the second. However, if it was doubles, then displacement unit would naturally be 8, because then you'd want the third entry to start at byte displacement 24. So that's some attempt at giving some kind of portability to this. You can specify no memory at all, and there are various subtleties, but really this is the important point, that you create, you allocate an array, and then you turn it into a window, which then makes it available for remote read and write through put and get with this call. And once you've done that, you supply a communicator, but the window now supplants the communicator. So all these RMA calls take windows as arguments, not communicators. So you could also query the window and free it. So there's lots of synchronization methodologies in MPI RMA, probably too many, but synchronizations are required to start and stop in eCoff. From a programmatic point of view, you need to synchronize globally before you start doing remote reads and writes to check that if you're writing data to somebody. So there's a question there. I'll answer that question at the end of the lecture. Is that okay? The first synchronization makes sure that if you're going to read data from somebody, it's ready, it's to be read, or if you're going to write data to somebody, they're not using it. And the second one, it's only after the second synchronization that the communications are guaranteed to be complete, because they're non-blocking. So it really follows, it's really like a barrier synchronization. You call it MPI win fence, assert on a window. So basically, you can't do RMA till you've started a fence, you issue the communication, all the communications block there. This 0 is an assertion. You can give hints to help the MPI implementation optimize things, but the default value is 0. It's just saying, I'm not giving you any hints. You can give hints such as, I am only going to do puts, I'm only going to do gets, and things like that, which might be useful for performance. So there are, you can pass lots of hints here, such as MPI mode no store, local does not opt over local rights of any form. But I mean, this is all really at the optimization level. We're not particularly interested in that here. So these are the RMA. So having created a window, you can then read data for a remote window with MPI get. It's like a receive, origin yes, origin count, origin data type, but on the target, which is where you're reading the data from, you give the target rank, but you give a displacement account. And so rather than as well as a count, you also do a displacement. So it's like doing it is a remote read, but you start at, you don't start at the start of the window, you start at a position target count. But it's a bit like, this is like the receive argument, this is the send argument. A put is exactly the same, except it goes the other way. You put data from the origin into the window of the target rank at a displacement starting at target count, target disp into the window. And you can actually accumulate if you want to, rather than write. If you want to add data, you can accumulate. So you can basically, for example, you might want to. The classic thing you want to do is to add 1 to a variable as a global counter. You can't do that with a get, add, put, because the get and the put are asynchronous. So if you do get, add, put, you don't know the get has completed it before the put, so it doesn't work. There's a special accumulation routine. But it's quite a simple model. Put and get or accumulate may be useful. And so, similar to non-blocking point-to-point, you have to wait for synchronization until you can retrieve the data. So you cannot access any of your data until after the second fence. Okay. And this is a bit like OpenMP. You start a parallel region, you end a parallel region with a barrier. You can't guarantee that everything is over or complete. You can safely access the data until all the threads, in that case, all the threads have completed their work. There are lots of ways this can be undefined, but we've seen the target displacement blocked by the window displacement unit, and there's lots of things that are undefined. The most, if there's a remote put going on, you can't locally read or write the window because you don't know if the put has happened yet. Puts to the same location. are all undefined. So it's up to you to make sure that you do the right thing. This is all because the order of the way that things happen is not defined. You issue the commands, then you wait. You know they won't necessarily complete the order you issued them. So there's lots of things which are undefined. So the generic simple approach: declare local storage on each rank with allocate in Fortran or malloc in C. Create a window including all the storage with MPI win create, and this window replaces the communicator. Then when you're doing calculation, you just access the data in local storage using normal array operations. You just read and write. Then when you're ready to do some communication, you synchronize so everyone is ready with MPI win fence. You issue remote reads or writes to or from the other data with MPI get and MPI put. Then you finish, you say everyone finished with MPI win fence, and then you can now access data in local storage as normal. So that's a very simple approach. And so there's an example here where what we're doing is, I mean, this is a very complicated way of doing something simple. We're basically doing a broadcast, but what we're going to do is we're going to create some data on rank 0, on rank 0, and every other rank is going to read the data with a get. So we have a master buff. We have to declare a window. We have a master buff, which is only going to be valid on the master or on the controller rank 0, and my buff, which is both the same size. If rank is 0, then I create the window with master buff. This is how many bytes it is, and this is the displacement unit. If I'm not, I supply no data to the window. Okay, so I'm basically supplying no null. I'm passing a null pointer. So although this window covers, this is a slightly complicated example, although this window covers all the ranks, only rank 0 is actually contributing any storage. So reading or writing to a window on a rank other than 0 is going to be undefined. If rank is 0, initialize master buff. This is just standard. This is just an array. Then we say, right, MPI win fence, MPI mode no proceed win. This says there have been no preceding RMA calls on this. So that means that the library doesn't have to clear up anything. You're telling you, look, this is a synchronization, but nothing has happened, so you don't need to check for any outstanding operations. That's why it might be slightly quicker. If I'm not rank 0, I will get, okay, into my buff 20 integers from rank 0, starting at displacement 0, 20 integers in win. So this is like the send, and this is like the receive. This is issued, and then it will happen asynchronously in a non-blocking way, but then we do an MPI win fence, actually saying there's going to be no succeeding operations on this, and then after we've done that, we can then process the buffer because we know we've read it. It is a rather complicated example, but it illustrates the point. You local allocation of data, stick it into a window, do normal reads and writes, fence, puts and gets, fence, and then carry on having transferred the data. So the model is quite simple, although the syntax can be quite challenging. Performance may not be very good. So to shoehorn, MPI was designed for matching send and receive. Here we've got send without receives, puts, and receives without sends, gets. It's not a natural fit, and MPI has a lot of not fault tolerance, but portability and resilience put into it. So there's an enormous amount of latency. So one of the reasons people think they want to do direct read and write is to avoid latency. Rather than have to match a send and a receive, you just write the data directly. However, in practice, you may not get as good performance as you think because it's quite hard to implement it efficiently in MPI. However, as I said, windows are a key component of the MPI shared memory approach, which I think is useful as a counterpoint or a companion to hybrid MPI OpenMP. It allows us to directly read. So the important point here is we've got windows which we can remotely access with direct reads and writes, but those reads and writes have to be through puts and gets. We have to access them from function calls. But actually, we just like on a node, we would just like to be able to read and write them directly, and that's what we can do with the shared memory approach. So that's the next lecture. So before I go on to that, just to give you a break, if I want to be asynchronous algorithm like those originally designed for GPU and distributed model, can I use RMA synchronization to mimic the behavior? I don't really understand what you mean by asynchronous algorithms designed for GPUs.
Okay, speak.
Do you mean Yeah, hi, yeah.
Hi, yeah. So a synchronous algorithm is like, for example, like I'm not sure you're familiar with, for example, like multicolor Gauss seidel, and then so for every color you have to swap the halo for
So
every
you
color
you
information.
color the domain to avoid data races. You're saying you colored it so that all the red points are independent from the blue points. Okay, yeah.
Yes, something like that. It's just that okay. So in GPU there's this asynchronous algorithm like um if the data has arrived, then I will use the new algorithm. If the data has not arrived, then I'll use the new data. If the data has not arrived, I use the old one.
Okay, so you're okay, fine. So okay, right. So you're basically, I don't, yeah, okay. So you've basically written an algorithm and then taken out the synchronization and just said, well, if the data's not arrived, I'll use the old one rather than the new one,
Yeah,
and
yeah,
cross my fingers and hope everything's okay.
I'll use the latest one that I have
Yeah.
to
I mean,
to move the information.
that's not necessarily a. No, that's a standard approach, and in the problem is that you could try that, but the problem is if you do a put, if you're writing data, you do a put, yeah. There's no guarantee that that will complete at all until you do the synchronization point. So
Okay.
depending on the implementation, it may work or it may not. I mean, technically, it's probably illegal to do that. What you really want to do there is to use something. The problem is that, yeah, without a subsequent synchronization, it's possible the data will never arrive. So now there are other lower level libraries which can help you there. There's a library called SHMEM or Gatsby, which do this kind of thing. And you can sort of you might get away with it, but I think with MPI it's not going to work because probably it will get unhappy if you never do a synchronization.
Okay.
I mean, you could do a synchronization every 20 iterations or something, couldn't you, just to make sure? But I don't think it's. If you're going to do these asynchronous algorithms in a distributed setting, you don't want all the guarantees and checks of MPI. You want something much lower level that just does, and you would use something like OpenSHMEM is probably what you would use there. Yeah. So yeah, yeah. Okay. I mean, MPI isn't really designed for this kind of thing. MPI is really designed to be reproducible and deterministic, whereas by definition, asynchronous algorithms are non-reproducible and non-deterministic. And just cross your fingers and hope you get the right answer. And I know you can prove that you get the right answer for some of these things, but that's not how MPI works. MPI is designed to be deterministic and reproducible. It's a good question. I understand what you're asking. Yeah, fine. So there are single-sided libraries which would allow you to do it, but you probably want to use something like OpenSHMEM or Gatsby and not MPI.
Okay. Yeah. How about I know like there's like parallel feature in Fortran, like the latest Fortran, like Fortran 2008 or
Fortran coarrays.
Yeah, Fortran coarray.
Again, Fortran is designed to be reproducible and deterministic, and so you have synchronization calls in coarray Fortran exactly analogous to MPI WinFence. It's called syncall, but to guarantee now, the data may have arrived before then. You don't know, but again, you might be lucky, you might not. But the language only guarantees the data is arrived after the synchronization call. So with no synchronization call, it may never arrive.
Okay.
So that's always your problem. Yeah.
Okay. Thank you.
Yeah. Okay. But it's a good question. So I'll now do the next. So we're going to take the concepts of window creation and fences, but not put, we're now, rather than using put and get to be able to read and write to anybody's memory, we're going to use direct read and write to the memory of each process, processes which are physically on the same node. So we sort of hijack the what's the word? The infrastructure of RMA. So let's get the final lecture, which is here. So I don't go through all the details here, but I give you an example of how to use it. So just a quick comment on the motivation. This is the diagram before, and I think this is the big disadvantage of MPI plus OpenMP, is, as I said, to reiterate, if I had a node of 6 CPU cores, in the pure MPI model, I run one process per node, so 6 processes. In MPI plus OpenMP, it is not that these processes magically become threads. I undersubscribe. I run fewer MPI processes than there are physical CPU cores. Here, 1. And it's only when I do a parallel region with OMP parallel that I use the other ones with threads. And so there's wasted computation here, and you have to parallelize your entire code. So it's not an incremental approach. You've had global effects on your entire code because you've run it on fewer processes. What MPI shared memory does is, in some sense, it allows these processes to basically behave like threads. In other words, share memory amongst each other. And that allows you to have a more incremental approach. You have 2 implementations of your algorithm, one using normal MPI, one using MPI shared memory, and plug and play them and see which one is quickest. So I think that's quicker. So I think that's a more elegant approach. The reason why this is a problem is that immediately when you go from here to here, you take a hit in performance, because this is now running a 1/6 of the speed. Okay, so the first thing that happens in MPI plus OpenMP is you take a massive hit in performance because you've unsubscribed the processes. So here's your pure MPI. I now only run on 1/6. I take this massive performance hit, and then as I start, this is developer time, as I start adding more and more OpenMP, parallelizing more loops, I climb up. But do I ever beat where I started? I don't know. Some people do report successes, but I don't want to go into the caveat. It's often not for the reasons that they claim. There are certain corner, I won't say corner cases, there are certain specific cases where this is very successful, but it's not a general panacea. So exploiting shared memory with the standard RMA, we publish local memory in a collective shared window. We can do read and write with MPI get put and appropriate synchronization, but this seems wasteful on a node. If I've got 2 processes on the same node and they've got this shared memory window, why do they have to use function calls which have got latencies of hundreds of cycles rather than, you know, hardware latencies of sub-nanoseconds? Why can't I just read and write directly? So you can do this. Technically, it requires something called the unified model. It requires that there's no distinction between RMA memory and normal memory. What it means is the worry is that there might be some systems where when you do RMA access in Windows, it's actually physically in different memory, which is different from the local memory. To be honest, in modern standard CPU architectures, memory is just memory. So technically, to use shared memory in MPI requires something called the unified model. But in practice, that is not. You can check that at runtime by querying the window and see if the model supports MPI Win Unified. But I've never found a system which didn't. So there we go. So the procedure. So first of all, only processes on a node can share memory. So we need to identify processes which share a node. So we need to join. So what we do is we create separate communicators for each node. So we have a separate communicator, one for each node. We then do shared array allocation across all processes on a node. It's a special routine. Each process receives a local array, but the operating system actually makes sure that it's a big array. So if there's 10 processes all ask for an array of length 4, what the operating system does is it makes an array of length 40 and gives each process a subset of size 4. So these little local arrays are actually just subportions of a global array. And that means, this looks very nasty, but to access your neighbors array, you just over or under index your local array. So local array -1 will be the last entry on the previous process. I've got a diagram to illustrate this. So that's actually quite nice. We need appropriate synchronization for remote accesses, just like we use barriers in OpenMP, we use fences here. And still, you need MPI calls for inter-node communication. You can't do this across nodes. But so how do we create node local communicators? Well, there's a special routine called MPI com split type, where you give it a communicator, you give it a split type, which is which we all use MPI com type shared, which means it says split the communicator based on whether we share memory. So this gives you a new communicator where all the processes on the same node are in the same communicator. Key allows you to order them, and there's various info you can do. I just use MPI info null. And if you pass your key as your rank, that means that the order in the new communicator is the same as the order in the old one. At least that's the natural thing to do. So this is a general routine MPI com split type to split on any type. Currently, I believe the only type that is allowed is MPI com type shared, but this is there for extensibility. In the future, you might want to say, you could be running on a heterogeneous machine which has CPU nodes and GPU nodes, and you might say, I want all my CPU nodes to be in, CPU processes to be in one communicator, and all my GPU, this might be a MPI com type accelerator or something, but we're going to use it with MPI com type shared. So an example, we've got 12 processes across 2 nodes, ranks 0 to 5 on node 1, ranks 6 to 11 on node 2. COM has size 12, and these are the ranks. If I call MPI com split type, passing com world, MPI com type shared, I use my rank as the key. That means they're ordered in the new communicator in the same order as the old one, and I get back a node com. Within node com, has size 6, and on node 0 the ranks are the same, but on node 1 my ranks are 6, 7, 8, 9, 10, 11 in com world, but 0, 1, 2, 3, 4, 5 in the node com. So this call in this case would split into 2 separate communicators, both called node com, where the first 6 processes are in this node com and the next 6 are in this one, and they locally have ranks from 0 to 5. So it's actually quite nice. This is also a useful routine if you want to do, I said previously that often you want to optimize your I/O. A nice thing to do is to do 1 file per, ideally you have 1 file per application. You don't want 1 file per process because that's horrible. But 1 file per just about livable with. And so how do you write a file per node? You need to identify which processes are on the same node. This MPI com split type is very nice, and it will achieve that. Now, to allocate the rate, as I said, this is so the normal way that you create windows is you malloc the memory yourself and then make it into a window. We can't do that here because remember I said this memory is special. Rank 0's memory is contiguous with the rank 1, which is contiguous with rank 2's. The memory on each rank is actually a subset of a big contiguous array. That clearly is something which we can't do ourselves. We need the operating system to do it. So there's a new win allocation routine. MPI win allocate shared is just like malloc, but you give the size, you specify the displacement unit again, which is the counting unit, the communicator, and you get back a base pointer and a window. So this window is the window which you could use in put and get operations, but this base pointer is the returned pointer. It's like the malloc pointer. So MPI when allocate shared, size disp unit info com base pointer win I error. This in Fortran it's a bit nasty. I have a comment on how to do it in Fortran. But basically the size of the window size in bytes, just like malloc. The base pointer is the allocated storage, just like malloc. You get like a window, and the displacement unit is the counting unit. Remember I said when you create a window you need a counting unit, which is typically the size of the base type. So 4 for integers, 1 for characters, 8 for doubles, 16 for double complex, for example. That would be the obvious counting unit. So the traffic model example, what I want to do is I now need a node com. Now let's assume I've created node com. So node com already is a communicator that holds all the processes that are on the same node. I have old road, but it turns out that I need to do, yes, I need to do send and receive, or I need to do remote memory operations on old road. So old road needs to be in a window. So I say the win size is n local plus 2 times size of int. Remember, we have halos. Displacement unit is size of int. So I do MPI win allocate shared win size, which is how much data I want. Displacement unit is 4. Node com. I get back the old. So I get back old road and the window. But the important point is old road is now a pointer, just like it was malloc, to storage, but it's special storage that my storage is contiguous with the storage of the ranks beside me, and that's what allows you to do remote read and write. So imagine we have n local equals 2, so our array is very small, so we have our local road is 2, and we have a halo on each side, so that's x0 to x3. Okay, if I wanted to access the halo data on node rank 2, I would call it x4 or x7, or this is x minus 1. So I'm allowed to over and under index my local array to grab data from other people. Looks a bit nasty, but it does work. You can actually relax, you can actually decide not to have contiguous data across processes, but I don't see why that's particularly useful. The default is a contiguous block of memory across processes. And so that is, really how you do it. How do you access another rank's memory? In the previous diagram, rank 1 can access rank 2's x0 by referencing its own x4. Sometimes I might want to have an array which is basically, I might like to know what that pointer is, okay? So I can just index it from there. It's a bit of a, I'll skip over this a bit, but it's a bit of a subtlety, but how do I find out what this pointer is? He's not allowed to send it to me. Well, he could, but the way that the shared and the physical and virtual memory map to each other means that pointers don't mean the same things on different processes. So there's a funny routine called MPI win shared query, gives us a local pointer which we can use to access remote data. So there are 2 ways of accessing remote data. One is to over or under index your local array. The other is to get a pointer which points to someone else's data. You can't do that by send and receive. You have to have a special, which is MPI win shared query, gives us a local pointer which points to the data that owned by a particular process. It's a slightly strange thing to do. Synchronization, we can now do halo swapping by direct copies. We can just read and write, but we need to ensure the data is ready beforehand and available afterwards. So we just use synchronization, MPI win fence. And so it's just like an OpenMP. In OpenMP, you bracket parallel regions with OMP barrier or begin end parallel. In shared memory MPI, we bracket our remote accesses, which are, remember, remote access means access to data which we don't really own, with fences. So to do halo swapping, so we now have a choice when we do halo swapping. I can either write my remote data into someone else's halo or read their boundary data into my halo. I've decided to write my data into the other person's halo. So old road of n local plus 1 is old road of n local minus 1. So write, so that's saying I'm writing that boundary data into there, and then old road of -1 is old road of 1. I'm writing that data into there, which is achieving the halo swap. And then I do a fence. So fence, local, remote, well, reads and writes to shared arrays, fence. It's just the same as model as OpenMP. So if this direct read write only works within a node, you still need MPI calls for internodes. So the natural thing would have node rank 0, node rank node size -1, call send and receive. Actually, because this array is globally accessible, you can actually use any rank to do this, but and you have to do this in MPI com world. Remember, node com, this is where you have to remember you're a member of multiple communicators. Node com only contains the processes on a node. By definition, you can't use that to send to other nodes. So the MPI calls take place in com world, whereas the RMA calls take place in node com or the associated window. So the conclusion: it's a relatively simple syntax for shared memory in MPI. People used to roll their own solutions with handcrafted shared memory segments, but it's horrible. Possible use cases: on-node communication without needing MPI, which I've illustrated here, or one copy of static data per node, not per process. This is a really elegant way of doing it. If you have a large lookup table which is replicated per node, it is really only a few lines of code to have a single copy per process. Which is replicated per process. It's only a few lines of code to have a single copy, which is only owned by, for example, rank 0 on each node, and that can save you a lot of memory. So that's actually, I actually considered writing a sort of a wrapper that basically just did this for you, but I never got round to it. But it is actually potentially very powerful. The advantages are it's an incremental plug and play approach, unlike MPI plus OpenMP. You're not making global changes to the program. The disadvantages are there's no automatic support splitting up parallel loops. There's no MP4. You have to, divide up by hand. And that's a good question, David. And the global array may also have halo data sprinkled inside. So if you look at this global array here, it actually has halo data in it, which is rather nasty. But it's because this is a plug and play approach, we're not affecting the rest of the code. So we still have halos on our local arrays, which isn't natural in the shared memory approach. So it's a bit of a hybrid. David says, does this index has custom lower upper bounds? What do you mean by custom lower upper bounds? Are you worried, David? You can do audio if you want. Are you worried that the array bounds checker will? So I talked about this. Okay, so if you look at the exercise sheet, that's a very good question. I came across exactly that issue in developing this exercise. And I'm confused now because I've lost my window. Let's go to where. So I'll share the exercise sheet because I have a comment at the bottom which hopefully addresses this. But I'll explain the issue. It's actually, the problem is not in MPI, the problem is in Fortran. I actually suggested that the Fortran standard should be changed, well, to somebody who's on the Fortran forum. So in Fortran, so basically in Fortran, this is what you do. You use this sort of ISO C. So the interface between C and Fortran now is reasonably well standardized. So you use. Oh, can you see my cursor? Can you? Yes, you can. So our shared array is what we end up with. Integer pointer dimension colon shared array. That's what we want to end up with. I think you need pointer. You might be able to do allocatable. I'm not sure. I'm not a very, what's the word? I'm not a very modern Fortran program, I'm afraid. But the winAllocate shared gives us a base pointer, which is a C pointer, which is useless. So we have to do call CF pointer to convert that base pointer into a shared array. The annoying thing is this call CF pointer is a stupid function because, and it's a Fortran function, it doesn't allow you to specify the custom upper and lower bounds. it insists that these go from 1 to n. So if you want to index from 0 to n-1, you need a separate set of pointers to point into this. And this is not MPI's fault. This is Fortran's fault, that the CF pointer routine is stupid. It should allow you to specify the upper and lower bounds, but it. Eric said, could you store C+ objects in the shared memory region? So once this memory is allocated, it's just memory. So yes, it's just a very, well, it's an MPI way of giving you a shared memory segment if you're a bit more of a hacker. But yes, it's just a pointer to memory. All that has happened is the operating system has made sure that all the memory from the different process. So it's special memory because you have to do nasty things with virtual. But basically it's just memory. But the operating system has just been kind to you and made sure that all the separately allocated sets on each process are lined up in. So what it will do is it will do a global allocation of a big array and split it up amongst the subarrays basically. So yeah, there's nothing. It's just normal memory. There's nothing. It's just normal memory. The only special thing about it is it's accessible from every process, the same memory, which is a bit. I think they use shared memory segments under the hood. Does that answer your question, Eric? I mean, I'm not really a Unix guru, but I don't see any problem with it. It's just memory. So you just pass the pointer in. That's right. Does that answer your question? Yeah, I guess so. That's a good question. What's the boost into process library? Yes, I think it probably does actually, but it also managing shared memory. I'm just Googling it. All these things are just interfaces to shared memory segments, which is the operating system way of having the same piece of memory accessible by different processes. Despite the fact the whole point about processes is they can't share memory, of course you often want to do it. So yes, it's that sounds like a good. I don't know much about Boost, but from 5 seconds of Googling, it is MPI's interface to the system shared memory library, and I'm sure that's all that Boost is doing. Does that help? So I mean, you can do this thing a number of ways. It's now defined in MPI. So it's reasonably, you can write a pure MPI program which does this without having to involve external libraries. Yeah. Yeah. So if we look at the timetable, luckily I'm on the right. So the original plan had been, I'm on time, that you could look at the shared memory model exercise till coffee. I mean, I think it's been quite a long day. I'm not planning now to be around online beyond 4, but I am more than happy to take questions afterwards. So if a question occurs to you after the course, feel free to email me. But it's been quite, it's summer. It's been quite tough. It's Friday. I thought we should probably finish it at 3:30. And if you're welcome to finish the exercises. The reservation will still be running, I think, till 5:30, at least till 5, so you can get rapid turnaround. But I won't be online to answer questions. But I will, more than happy. Yeah, so Giovanni, I'm happy to have a quick chat. Yeah, fine, no problem. We can do that. What I will do basically is, well, actually, I've shown you the code. So if you look on, I will now just go back to my Archer account just to get. It's really not happy. Oh, there it goes. So if you look, I'll do the C versions just for so the C RMA. Oh no, that's not what I haven't actually. So I now have put up the solutions to these exercises. Let's find them. So it's called traffic RMA.tar. It may actually unpack into the same directory. It's a bit naughty. Oh no, go to RMA, see MPI RMA. So this is just the same traffic code, but if we look at traffic RMA.c, this uses remote memory access puts and gets. So this code is all the same as you've seen before, but I now have windows and win sizes and displacement units. And in this situation where we're not doing shared memory, we can just do normal allocs. We allocate the road ourselves, and then we tell MPI to create a window from it. And that's fine because there's no, we're going to use puts and gets function calls to access this data remotely. So it doesn't need to be lined up in memory. It doesn't need to be specially allocated. And then previously, now the send receives are replaced by a fence to synchronize, a put for one halo, put for another halo, and then another fence to synchronize. You could use gets, but I've decided to use puts here. And the rest is just the same. All I've done here is I've done the communications with put and get, the halo swap. I still just use the normal ordered reduce. So hopefully that's reasonably clear. This is just a very, very simple example of how to do puts and gets. As I said, we have to do two things. We have to make the arrays available for remote memory access by creating a window from them, from old road. It's only old road which I need, and the disk unit is the size of int. And so this call here says, this call here says put old road local of 1, which is 1 MPI int, to offset 0, which is integer number 0, on rank up. This is a bit restrictive. Write my lowest boundary data into the n local plus 1th entry in this win, which turns out to be the n local plus 1th integer in the other guy's old road. And the equivalent for shared memory, it looks very similar, except we now have to have a node com and a few other bits and pieces. We now can't allocate old road. So first of all, we have to create a node local communicator, MPI com split type, com world com type shared node com. I then do a bit of debugging to say, you know, rank blah in com world is rank blah and node com on node blah, just to kind of check. MPI get processor name is your friend here. It gets you the node name of where a process is running. And then we now can no longer malloc old road. We need to do a special MPI win allocate shared. So disk unit size of MPI win allocate shared win size, which is this thing here. Disk unit is within node com, old road node win. I'm actually not going to use node. Oh, no, I do use node win. I do the synchronization on node win, but the reads and writes to old road. So this is the shared array, but I still need the window because synchronization is done on the window, not on the array, which is a bit weird, possibly. And so if we look at it here, it's all the same except here. Right, MPI win fence, old road n local to the old road n local. I have to be careful if I'm the last guy, okay. If node rank, if I'm node size -1, I'm at the end of the road, and literally, and I need to actually do a send or a receive. So only if I'm node rank is not equal to 0, I can write off, and that's the local stuff done on a node, and I still have to do a send receive. But I do it like this. Node rank is node size -1, node rank equals 0. So there now you can see that there's explicitly different communication between the processes in a node and the processes between nodes. But there is only one send receive per node. And the stuff within a node isn't done through OpenMP, but it's done through halos, but the halos are basically, you see, this is over and under indexing my array. So that's basically the way it works. It might take a while, but that's the sort of philosophy of it. And I think that, you know, probably if there was one easy win, the most powerful is if you have a shared data structure. This is a very, very simple way of having one data structure per node. Sorry, I've got an infestation of flies here. One data structure per node rather than one per process stroke CPU core, which can be a vast saving in memory when you have 128 nodes. Sorry, 128 CPU cores per node. So I'll stop sharing now. And if there are any questions, I'm happy to take them. I saw that I had a request for a one-on-one chat, so I'll just give me, Jovi, give me 2 minutes to get a glass of water, then I'll be back, and we can. If any questions, I'm happy to answer. I should check if there's been any more questions on the. No. So actually, before I go, I should just say I hope you found it useful. I realise it's a bit tough, but you will be getting a questionnaire from Claire. You may have received the reminder, I'm not sure. Please fill that in. As I always say, good feedback is great. It makes us feel good about ourselves. We can tell absolutely how wonderful we are. But poor feedback is also essential. We review the feedback regularly at weekly meetings, and that allows us to improve the courses. And the feedback is by default anonymous, so you can say what you think. So thanks, everyone. And I'm going to be around the next half hour, but if you're leaving or whatever, have a nice weekend. Enjoy the weather. If you're in the UK, it's fantastic weather. The weather looks, I mean, I've been seeing reports from Central Europe, Germany. The weather looks awful there. I hope no one's affected by that. But at least if you're in the UK, as I remember most people were, it's going to be, well, for us, very hot. I think if you're in Central Europe, you don't think that 22 degrees centigrade is hot. For a Brit, it's steaming hot. So I'll be back in 2 seconds. Oh, Matthew's self-isolating. I'm really sorry to hear that. Okay.